Okay, so hello. For those of you that don't know me, I'm Aggie, and I'm a PhD student in Oxford working with Dimitri and Alex Wierzchucka. And today I'll talk to you about some of the results that we've been working on this year on basically synchrotron-Cooling-Unstable relativistic plasmas. So first things first. Oh, how does the... Is it click? Oh, it's just like, there we go. Anyways, so let's quickly for some background. Obviously, the distribution function of some species, which is susceptible to synchrotron cooling, will satisfy the Vlasov equation plus this extra correction on the right, which would be the Landau and Lifshitz radiation force, which obviously takes care of the synchrotron cooling. For the case of ultra-relativistic positrons or electrons, which is kind of what we're mostly interested in, it simplifies to this form. But if you consider the case when the electric field is 0, you can again rewrite it in a more simpler form, and that way we can then define a significant cooling time. That's going to be important in all our simulations. So let's kind of start easy. Let's start with some sort of ultra-relativistic Maxwell-Eutner hot species, right? And, you know, in this limit, this is what this distribution function looks like. So let's kind of go back to our Vlasov equation and integrate the last term to see exactly how the pressure of this relativistic Maxwell-Eutner is going to vary as it cools. But of course, this doesn't capture the whole story, because on the last slide, you could see that the radiation force actually had a pitch angle dependency. So even though here I've just got this kind of easy-looking cooling term, what actually happens is that this pitch angle dependence means that particles with large pitch angles are cooled preferentially, so over time you will get a negative pressure anisotropy, right? And of course, what does negative pressure anisotropy mean? Well, as Archie talked about in his talk, when you have negative pressure anisotropy, you're going to have a fire hose instability. So really recently, Vladimir Zhdankin looked at this in a lot of detail, where he basically started with a setup with some sort of background magnetic field and let it go. Initially, the electrons and the positrons, well, we studied it for the species combinations, but let's just focus on that one. The electrons and the positrons had an initial Maxwell-Eutner distribution, and what happened is, as I described in the previous slide, the distribution cooled, a negative pressure anisotropy arose, and you get a fire hose instability, simply just by equating this pressure anisotropy to the fire hose threshold, which is 1 over beta. And as what fire hoses usually do is they grow, eventually they get big enough to scatter particles, and they isotropize the distribution function. So what happens, right, is you get this Maxwell-Eutner distribution that cools, gets a negative pressure anisotropy, fire hoses arise, isotropize it, and you're back to the start, so you keep getting more and more fire hoses. So if you look on timescales longer than this sort of pinning, this time on which these fire hoses are actually pinning this pressure anisotropy to the fire hose threshold, you're going to see an isotropic distribution function. But of course, the whole reason why I made a point of integrating this Maxwell-Eutner and finding the decrease of pressure due to the cooling, ignoring the anisotropy, is because synchrotron cooling plasmas are also unstable to fluid instabilities. So if we just sort of take a very simple model of cooling collisionist pair plasmas, again, make our lives really easy, so just make them relativistically hot. We take our bulk flow to be non-relativistic, we make our plasma highly magnetized, and then we take our cooling to be very slow. So then we can propose this sort of fluid model where at the top, we've got the continuity equation, the induction equation, the pressure balance condition, and then we have two other adiabatic laws, which, I can go into in more detail offline, because there's a lot of relativistic kinetic MHD that goes into it, but for the point of astrophysics, I'll just write some pretty equations down, and then everyone can just look at how simple they are. But anyway, so we've got this fluid model, and now let's take this fluid model and, see what properties it has. So, homogeneous solution, let's just, again, like Vladimir Zhdankin, consider a magnetic field in the y direction, solve the equations, and we get that we're going to have cooling, right, as, you'd expect. But now, let's take this homogeneous solution and perturb it. So, these perturbations are going to be perpendicular to the magnetic field because I'm setting my magnetic field to be in the y direction. So I'm going to consider these perturbations on timescales much slower than the cooling time, in a way that this overall cooling is just going to be some background that I'm not really interested in at the time, just kind of to see what happens on top of it. And if I linearize the equations that I showed on the previous slide, you get a growth rate that looks like this. So clearly, if beta is larger than your magic number of 4, you get a instability, which is called the synchrotron-cooling instability. So a very easy way to kind of illustrate how this instability works is you get a region where you've got a high magnetic field. That region now cools faster if you go back to the expression on the cooling time. So in that region, your thermal pressure is going to decrease, but because the whole system is in pressure balance, that must then increase your magnetic field pressure to keep the pressure balance condition, and it closes the feedback loop, and you get an instability. And as you kind of would expect, it would continue until beta is of order 1, and if you do the calculation, it turns out that the magic number is 4. So what did I do? So we've got these, kind of take a step back, we've got these fire-hose instabilities and the synchrotron-cooling instability. And obviously PIC is intrinsic truth, so what I did is I did a PIC simulation. And I essentially started with some sort of homogeneous plasma, Maxwell-Utner electrons and positrons, and then I gave it a little perturbation in the magnetic field just to see what would happen, because that would excite the synchrotron-cooling instability and the fire-hose instabilities. It's very important in these simulations to make sure that my cooling time is set such that it's much smaller than the gyration time, so that the fire hoses actually have time to grow, develop before the cooling would just cool the whole system down to betas of order 1, right? So I do this, and I showed this kind of naive fluid model, but this fluid model fits the PIC simulations very well. So you can see that even though, as I'll show in the next slide, lots of crazy stuff is happening, well, not crazy, but lots of kind of turbulent stuff is happening, the fluid model fits very well. And the gamma factors, the adiabatic indices that I sort of just introduced as some sort of fiducial parameters, the value of it that I get that matches the best is 1.5. There is a kind of physical explanation why that is, but for the sake of keeping this short and sweet, I won't go into that. Okay, but now let's look at the fire hose structures, what these fire hoses look like now when we have the synchrotron cooling instability in the background. And you basically get a kind of a two-phase medium, where on the sides, as you'll see, you're going to have fire hose instabilities. But in the middle, because your synchrotron cooling instability has generated this region of high magnetic field, you're not going to have the fire hose instabilities. They're going to get completely shut off. So you end up with this two-phase medium, where on the side you get pinning of fire hoses, pinning of the pressure isoentropy to the fire hose threshold, because that's the main effect of the fire hoses. And in the middle, because you're now in the middle, you've got really low beta, you don't have fire hoses. So in the middle, your pressure isoentropy can just grow really, really big. From running the fluid simulations, what happens, like the end state is that eventually in the middle you reach beta of 4, your synchrotron cooling instability stops, and then the end is going to catch up with it. So there's some lifetime I'm yet to calculate of this kind of, I guess, filamentary structure. I haven't ran the PIC simulations long enough to see what happens, because I suspect that if you've got this really high pressure isoentropy, something at some point is going to have to break, right? But anyway, so why do this whole thing, right? It's a bit of a random thing to do. And it's because there's these things, both in the ICM and the galactic center, called filaments that no one really knows how to explain. Because they're very long and thin and kind of really straight. So there's kind of a lot of theories about it. There's Kevin Helmholtz, MHD turbulence, but the point is that with all of these theories, they shouldn't be as stable as they are. So I'm sort of proposing the synchrotron cooling instability with these fire hoses as a model for these galactic filaments and the ICM filaments, because apparently from the papers I've read, it's sort of a similar process that's going to govern the two of them. So, I mean, based on the kind of simulations that I have, is you've got the fire hoses on the side and then this low beta region in the middle. So that would kind of give a natural, I mean, it looks like a filament, so must be a filament, right? So if you now send particles down it, you can see that because on the side you get these fire hoses, particles would be scattered crazy on the left and right, but in the middle they'll just stream through it. So that's why I propose that as some sort of a model for the galactic filaments. But anyways, I guess I kind of speak fast. So this is my summary slide, and this is sort of, I guess the main part of this is, we propose this fluid model that even though this whole thing is really complicated, right? Because anything with relativity is just a nightmare to do, apart from PIC simulations, because they're obviously easier. But this fluid model fits really well with these PIC simulations, which allows us to study it in more detail without running these really long PIC simulations. So, we end up with this two-phase medium, fire hoses on the side, no fire hoses in the middle. And I guess one big plot that Dimitri really likes is the summary of the timescales, with where the fire hoses start, how the fire hoses regulate the pressure isoentropy, and the timescale on which the synchrotron cooling instability starts to modify the magnetic field. But that's it. So I'll leave this slide up. But I guess if anyone has any questions.
Thank you. The room is open for questions. Yeah.
A great fast talk. I have two questions. One of them is, how do you scale your simulations to actual the filament? Like, is it happening locally in some portion of the filament and then it's getting like scattered throughout the whole thing? Or like, do you have any local, like your time scale? Like, how does it actually project to this filament? And also, what would you expect to see in 3D?
Oh, okay, so that's two very good questions. So first of all, so my simulations are local simulations. There's some papers, I don't remember the authors, but one of them is Matt Kunz, where it's not synchrotron cooling, it's I think it's inverse quantum or something like that, where they kind of force a box and they're global simulation, and you do end up with these sort of filament structures. But this is a global simulation where we actually propose a model for how we would describe these filaments in the case of relativity. But no, I'm yet to I need to sit down and actually do all the astrophysical calculations, because they are things that have been done. They are things that have been done in other papers, but I haven't got to that yet, just because I've been focused on the PIC. What was the second question? Oh, 3D. So in 3D, I suspect it would still be the same. I suspect that you'd still get these filaments. The question is, however, how stable would it be, right? So let's say that you start with this box, and then you put lots of these filaments in it, right? And then you add some sort of turbulence on top. Would these filaments still remain to be straight? And I am planning to do some 3D PIC simulations, but it would be really interesting. I mean, it would be even more interesting to include conductivity, because I think then you actually have something limiting the size of your filaments. But I think in 3D you still get these structures, but the stability of them would be something that obviously I have to kind of try and have a look at.
Okay, Archie and then Lorenzo.
Thanks, Aggie, for a nice talk. Would you mind going to your final slide? I had a question about the timescales. So presumably, depending on the relative size of your beta and tau naught divided by your tau gyro time, the kind of whether the fire hoses kind of grow very quickly or very slowly compared to, so that basically the relative size of those two timescales, you might have different behavior. Have you found anything like that?
Well, I haven't tried anything like that. I haven't tried anything yet. I mean, I've ran some really small simulations where the fire hoses don't arise just because I make the box so small that they're not resolved. And what happens is you will get the synchrotron cooling instability, but with sort of a different adiabatic index, because these fire hoses are not happening. I mean, the simulations aren't great because it's a very small box. But I haven't tried simulations where the beta, where I've kind of messed around, because I mean, this one and this one are kind of concrete. But if I change this one and this one around, then it would be kind of. I mean, I suspect if you change them both, you get the same situation, just no fire hoses on the sides.
Yes, because astrophysically, I think that time in the middle would presumably be much shorter potentially than the time scale on the left. When the fire hoses starts, because beta's large but not so large, whereas T gyro is very, very short.
I think if you have quite a large beta, it is. I mean, I have to check. But
we can chat after.
Yeah.
Lorenzo?
One is just a clarification. The composition of your PIC simulation is
per plasma.
Per plasma. And I mean, how much would you I mean, these are galactic filaments, right? So it's unlikely that the pressure is going to be dominated by a pure pair plasma composition. So the ions would provide pressure support and inhibit maybe the magnetic field compression that you do have. I don't know. I was just wondering whether you can comment on that.
So if you have ions, what's going to happen is you're still going to have this sort of instability in the electrons. The beta that you're going to reach, the smallest beta you're going to reach in the middle is, of course, just going to be the ion ones, right? So if you start with betas equal 20 electrons and betas equal 20 ions, you're just going to end up with total betas equal to 20 in the middle, because the ions don't radiate. If, however, you start with like really cold ions, well, you can explain this whole thing really easily using MAGD, because that's kind of how people initially discovered it. And if you have really cold ions, of course, it's always going to be ions that are limiting the smallest beta that you can have in the middle. So I guess then other instabilities, well, I guess because then you can have like ion fire hose instabilities and stuff like that, right? Because
but not induced from synchrotron.
Yeah.
The other question was whether you can have a prediction on the emission ratio between the filament and the surroundings. I mean, in principle, from your PIC, you have everything, right? So you could say, okay, this is how much synchrotron the magnetized region makes versus the outside.
Yeah, so I have a theory of that I'm kind of trying to make better. you know, so basically like an app, right? So in your app, you put like, okay, I start with a perturbation this big, a beta this big, how big is the contrast going to be? Because that's ultimately the question that astrophysicists are going to ask. And I have a sort of like a theory that I'm not 100% sure about, but it does kind of, I mean, I'm not 100% happy with how rigorous it is, but it is something that will be in the final paper, just maybe not now in these slides.
There's also a question online, so should we take a question online first?
Thank you for this chance. I've got one comment and one question. So I've conducted like 3D MHD simulations for the synchrotron cooling instabilities, and my observation is that, well, the instability is fully elongated to the magnetic field lines. So because the unstable mode is for the wave number perpendicular to the guide field directions. So that is almost identical to what the presenter just showed. And I've got another question, that is from the linear dispersion relationship, that is the instability growth rate will saturate to the small wavelength fluctuations. So have you ever observed any kind of cutoff instability growth rate after introducing the Firehose instabilities in the simulations?
Sorry, what was, so the question, the final, I can't, so the final question was what?
Yeah, so, well, in MHD regime, in MHD approach, the instability growth rate will saturate at small wavelength fluctuations, right? Mm-hmm. So that in my MHD simulations, I always observe that if the instability is dominated by small scale fluctuations, right? Actually, it is limited by like the MHD resolution, MHD cell size. But after considering like Firehose instability, well, it adding a cutoff of the synchrotron cooling instabilities in wavelength.
So the thing is, because I don't have any conductivity in these simulations, if I did an MHD simulation of the synchrotron cooling instability, unless I add conductivity, there's not going to be anything to cut off. Like the more cells I add in my simulation, the more groups I'm going to have here. But if I do the fire hoses again, I don't think, like if the fire hoses were providing some sort of a conductivity, which I could then calculate, then you know, that conductivity is going to have a corresponding wave number, and then that wave number is that thing that's going to limit the size. I think that's what I'm trying to say. Because if there's no conductivity, then there's nothing to limit how small these filaments can get.
So you suppose that there will be a cutoff for the for the synchrotron cooling instability, right? Yeah.
I think maybe we should keep this discussion offline through email. Dimitri, you want to make a last comment?
Thank you, Agi. Just a quick comment that in addition to the talk, Agi also has a poster over there with all the details of this work. So please come and talk to her.
Okay, we should thank Agi and all the other speakers today, this morning.